Thank you very much for the invitation. It's a great pleasure to give a talk at this conference for the second time. So the title of my talk will be Determination of quasilinear terms from restricted data. So here in this talk, there will be several notions that I would like to clarify. The first one being this idea of determination of quasilinear terms and the class of quasilinear terms that we would like to consider here. And the second notion, which will be the most important one, being the one of restricted data. So I will try to clarify all this notion through this talk. So let me start with the statement of our, sorry, can you see it, Katya, or there's a problem? Okay, so I cannot see it on my side. Okay, so let us start with the statement of our problem, where, okay, this is maybe the reason why I cannot see it. Okay. Where we will consider omega to be an open-bounded and smooth set of Rn, n being higher than 2. In this open set, we will consider the following equation, which will be an elliptic type of equation that we will consider on omega, involving an expression which will be some matrix valued function, which will depend on the solution of the equation, the solution being given by you. So this is the class of elliptic type of equation that we consider on this open set omega. And we associate with this equation the following boundary value problem by fixing a Dirichlet boundary condition at the boundary of our open set. So here, the class of Dirichlet boundary condition that we will consider, and the one that we will consider all along in this talk, will be taking values in real valued affine function. So this is the class of boundary value problem that we would like to consider. And the first thing that I would like to emphasize is that here we deal with quasi-linear elliptic type of equation. And the fact that we deal with quasi-linear and not linear comes from the dependency with respect to the solution of this matrix valued function, A of index I and j. So here we deal with this type of quasi-linear elliptic equation. And our goal will be the following one. So we will pick M point located at the boundary of our open set omega. And we will consider, by means of this M point, the inverse problem of determining this quasi-linear term. So the unknown of our inverse problem will be this quasi-linear term, this matrix valued function, that we would like to determine by means of measurement of the conormal derivative of the solution of this boundary value problem located at this M different points, and solution that will be considered by means of excitation corresponding to this Dirichlet data, which will be lying on this set of real valid affine function. So this is the class of inverse problem that we would like to consider. And our goal will be to derive both uniqueness and stability for this inverse problem. So let me say a few words about the motivation of our problem. And the first thing that I would like to say is that here our goal will be to consider the problem of determining a nonlinear term appearing in an elliptic equation, which has received a lot of attention among the mathematical community. So there has been an important interest in that direction. So here, in terms of physical motivation, we can mention the idea of recovering the conductivity of a medium by applying voltage and making measurement of the current flux. And the idea of considering this class of medium associated with a quasi-linear term can come from situation where the transfer from voltage to current is not given by the classical Ohm's law, but a more general nonlinear law associated with this type of quasi-linear term. Can also consider this type of inverse problem in the context of problems of viscous flow, but also plasticity phenomena. Finally, we can also mention the idea of considering this problem in the context of problem of heat conduction, where you will have the heat conductivity, which will be given by our quasi-linear term. And in our situation, it will depend both on the temperature and on the thermal gradient. And the idea will be to determine this heat conduction by means of measurement of the flux associated with different type of heat source applied at the boundary of our domain. So this is the physical motivation of our problem, but there is also mathematical motivation in the statement of our problem. So the main goal here will be actually to consider the determination of this problem with this notion of restricted data that I have introduced. This idea of restricted data will be more well understood as soon as I will introduce or recall what has been done so far for this inverse problem. So here we would like to consider two important restrictions on the data used so far for this class of inverse problem, corresponding first with the idea of considering restriction of the Dirichlet excitation lying on the space of real valid affine function, which is a space of dimension n+1. So here we consider excitation lying on a finite dimensional space, while as you will see, all relative results have considered excitation on an infinite dimensional space. And then I will explain a little more how this can be interesting if you, for instance, consider the problem for linear equation, since in the context of linear equation, excitation lying on a space of finite dimensional space will correspond to finite number of measurements, which is, of course, not the case for nonlinear equation. So this is the first restriction that we make. The second one being that we localize our measurement to at most endpoint. So we will see that actually this idea of at most endpoint will be either 1 point or endpoint, depending on the type of quasi-linear term that we would like to determine. So this is the two important restrictions that we make on our data. And actually the goal of that is to being able to move from this theoretical result to the numerical reconstruction. So this is the most important idea through this motivation of making restriction on the data used for the determination of quasi-linear term, because actually, as I will recall it a little later, this type of result have been mostly restricted to theoretical result. And the idea would be actually to have theoretical result that can be useful for the next step, which will be the numerical reconstruction, where actually it is quite difficult to compute numerically what is often considered in the theoretical result, namely something like the Dirichlet to Neumann map, which require too much data. So here our goal would be to consider some restriction on the usual data in order to be able to move to the next step, which is the reconstruction, numerical reconstruction. So this is what we can say about the motivations. And now let me recall the position of our problem, and let me give a little more information about the class of quasi-linear term that we consider here. So here, first of all, we make some minimal assumption of regularity on our quasi-linear term, and we impose some kind of ellipticity condition plus a symmetry condition. So here we have a map A that will correspond to our coefficient or our quasi-linear term, which will be a matrix valued map, and taking values in symmetric map, plus the additional ellipticity condition that we consider here, which will be rather a general ellipticity condition in the sense that this coefficient will be actually a function depending on these two variables, the variable mu being associated with the solution of the equation, while the variable eta will be associated with the gradient of the solution. So it will be some kind of general quasi-linear term. And after that, we can rewrite our boundary value problem as follows. So first of all, we consider in a simpler way the equation that we consider, in the sense that we incorporate in our equation this matrix A. And we introduce actually the class of Dirichlet data that we will consider here. Dirichlet data that will depend on two real parameters, lambda and tau, plus omega, which will be lying on the unit sphere. So this is the class of Dirichlet data that we impose. And now we can reformulate our inverse problem as follows. So we pick m point at the boundary of our open set, m being less than n. We fix epsilon to be sufficiently small, and we consider the determination of our quasi-linear term A from the knowledge of the conormal derivative of the solution of this boundary value problem for the parameter lambda along the real line, the parameter tau sufficiently small, and the parameter omega on the unit sphere. And so here, what I would like to emphasize is that in contrast to some of the work related to this problem, our Dirichlet data is not necessarily small. So there's no smallness imposed to our Dirichlet data here in terms of size, because lambda can be arbitrarily large. Okay, so this is the position of our problem. Now, let me recall what has been done so far for this class of problem. And for this purpose, let me recall some quite classical results related to this type of inverse problem, corresponding to the statement of this type of inverse problem from what is called overspecified data. So in this category of result, we deal with omega, an open set of R2. So the dimension of the space is restricted to 2. And the goal here is actually to determine a quasi-linear term depending only on the solution. So the statement of the problem is different from the one that I've stated before, in a sense that here the idea of excitation will not be given only at the boundary of the open set, where we will impose excitation given by the Neumann type of boundary condition, but also some kind of internal excitation given by the right-hand side term, which can be seen, for instance, as a source term. So we will have both internal excitation and boundary excitation, but single one, not an infinite number of them, just single excitation, both internal and at the boundary. And the measurement under consideration for determining this quasi-linear term will be the knowledge of the solution at the boundary. So actually, this class of statement of this type of inverse problem are quite old. They go back to the work of Kian of 1967. A result which has been stated initially in this work of Kian, but for which the first uniqueness result, first theoretical uniqueness result, goes back to the work of Pilon and Rundle. Not first one, but at least one of the well-known one is the one of Pilon and Rundle in 1988. So this problem has been treated in terms of theoretical result, at least theoretical uniqueness, but it has also received numerical reconstruction. So there has been numerical reconstruction formula associated with this type of result, including the work of Kugler, 2003, but also Egger, Pitchman, Scott Bloom in 2014. So for this type of formulation, we have both theoretical, but also numerical resolution of the inverse problem. But this problem is not exactly the one that we would like to consider. So now let us move to result related to the problem that we would like to consider. So for this, I will consider general class of quasi-linear term having several dependency, including space dependency, dependency with respect to the solution, and dependency with respect to the gradient of the solution. So the elliptic equation, as we have seen before, can be written in the following way. And we impose here a Dirichlet data from which we associate the conormal derivative of the solution of this problem, allowing us to introduce the Dirichlet to Neumann map. So here, consider a partial Dirichlet to Neumann map in the sense that the conormal derivative would be restricted to S, S being an open set of the boundary of our domain. So now the idea will be to consider inverse problem of determining this type of quasi-linear term from the knowledge of the corresponding Dirichlet to Neumann map. This is the type of result that we can connect to our problem. And in that category, we can start with some work that goes back to end of 90s until beginning of the year 2000, including the work of Sun of 1996, where Sun treated the determination of a real-valued quasi-linear term depending on the space variable and on the solution. The result which has been extended by Sun and Ullmann into the determination of a matrix-valued quasi-linear term depending on the space variable and on the solution. This in the case where the dimension of the space is 2, or the case where the quasi-linear term is analytic both with respect to the space variable and the solution. In the specific case of dimension n equal to 2, there is also the work of Harbas and Sun, who treated the determination of a matrix-valued quasi-linear term depending on the space variable and on the solution, on the space variable and on the gradient of the solution of the equation. So this is the first category of result that we can mention. For result dealing with the determination of a quasi-linear term depending both on the solution and on the gradient of the solution, we can refer first to the work of Shankar, but also Munoz and Ullmann, who have treated the case of a real-valued quasi-linear term depending on the solution and on the gradient of the solution. And for more general class of quasi-linear terms, still being real-valued, but depending on the space variable, the solution and the gradient of the solution, we can first mention our general results with Kartesa, Faiz Mohammadi, Krupschik, and Ullmann, where we have actually determined some general class of quasi-linear term combining this three class of dependency, giving actually by the same way a positive answer to an open problem which has been initially stated in the work of Sun and Ullmann, and a partial data result that we have obtained with Krupschik and Ullmann, where we have not considered the quasi-linear term fully depending on the gradient of the solution, but the gradient of the solution on a specific direction. So all the results that I've mentioned so far have been only uniqueness results. In terms of stability, there is not so many results that have considered this type of problem. And one of them is the one that I've obtained in work of 2023, where I have restricted the analysis to a quasi-linear term, depending only on the solution. And it was a partial data result in the sense that the measurements were considered on an arbitrary subset of the boundary, and the stability was Lipschitz. So this was the situation for this type of problem. I would like also to mention this series of work to a problem which is not exactly the one that we consider here, but which is connected, related to inverse problem for the minimal surface equation, which can be seen also as a determination of the quasi-linear. So this is what has been done so far, or an idea actually of different results obtained in the direction of determination of a quasi-linear term. And the first thing that we can say is that, as far as I know, there is no numerical result associated with this theoretical result. All these results are theoretical. There has been no numerical result in the direction of what has been considered by this different contribution. In addition to that, even in the category of theoretical result, what have not been considered so far, at least in the dimension n higher than 3, maybe in n equal to 2, it could be done, is the determination of a quasi-linear term, matrix-valued quasi-linear term, depending both on the solution and on the gradient of the solution. So here, our goal will be not to give actually a numerical result associated with this problem, but try to get close, but also to prove a result dealing with the recovery of a matrix-valued quasi-linear term, having these two classes of dependency. Okay, so let me come back to the statement of our problem. And the first thing that I would like to consider here is actually suitable condition guaranteeing existence of solution of this boundary value problem and sufficiently smooth solutions, allowing us to define the conormal derivative of its corresponding solution. So here, the idea is that for every fixed lambda, you can choose tau to be sufficiently small in such a way that this boundary value problem admits a sufficiently smooth solution. So provided that this parameter tau is sufficiently small, and the smallness which is conditional to this parameter lambda that we have fixed, you will have access to a sufficiently smooth solution. And actually, this solution will be unique. It is not uniqueness of small solution. This solution is unique. This is given by comparison principle. And then, thanks to that, we can consider our problem with this class of solution, whose Dirichlet data will be nothing but a function depending only on this free class of parameter, lambda, omega, and tau. This free class of parameter appearing in this class of real valued affine function that we have defined, with the parameter tau being the only parameter that can be small. The other one, lambda can be large, and omega is on the unit sphere. And our goal would be to treat the determination of the quasi-linear term A for the conormal, from the knowledge of the conormal derivative of the solution of this boundary value problem for this different set of parameters admitted such variation, and the measurement located at this m different point, m being less than n. So this is the situation. And before giving the statement of our problem, I would like to mention what will be the class of admissible quasi-linear term, because here actually we cannot determine anything. We will need some restriction in addition to the one that I've presented before. So this is actually technical restriction. And in addition to that, we cannot localize our measurement anywhere in the case of matrix-valued quasi-linear term. And I will specify what would be the point where we will localize these different measurements. So the first thing will be actually to consider the class of admissible quasi-linear term, which will have some specific type of smoothness. And the technical assumptions say, roughly speaking, that this matrix valued function with text values in symmetric matrix, and therefore admit an orthogonal basis of eigen functions, will have actually an orthonormal basis of eigenfunction depending only on the solution of the equation, not on the gradient. So roughly speaking, this means that we consider this type of quasi-linear term where actually here you have a diagonal matrix where you will have all the eigenvalues of the matrix, which may depend on the solution and on the gradient of the solution, but the corresponding orthogonal matrix that will allow us to have this kind of decomposition of our matrix will depend only on the solution of the equation. Also, the order of the eigenvalues will be independent of the solution, variable associated with the solution, and the gradient of the solution. So this is actually a technical restriction that we need to impose for the class of quasilinear term that we want to determine, which includes several situations, several different situations, but at least can include the case of diagonal matrix, depending both on the solution and on the gradient of the solution. So this is the simplest case where this appears, but this can be fulfilled in different situations. And what happened is that actually this is only technical restriction that we impose, and it's the only technical restriction that we will consider here for the class of quasilinear term that we would like to determine. So apart from that, we impose also a condition on the set where we consider our measurement, this different point, the n point. Here we will consider it to be m equal to n. M equal to 1, we will see it a little later on. For m equal to 1, there will be no condition. So here we assume that this different point are chosen in such a way that if you pick an orthonormal basis of Rn, each of these points computed at the outward unit normal vector of our domain will be sufficiently close of each of the vector of this orthonormal basis. So here, actually, this condition will be given with some estimate with a precise bound, the bound being given by 1 over square root of n being the dimension of the space. So we have this kind of specific closeness of the outward unit normal vector at this different point that we compute with each vector of this orthonormal basis. So actually, one question that you may ask yourself is what guarantee actually the existence of this endpoint, and what guarantee the existence of this endpoint will be actually what is called the surjectivity of the Gauss map, saying that the outward unit normal vector that is seen as a map going from the boundary of your open set to the unit sphere is surjective. This is a classical result that actually I was not aware of, and I learned it. And thanks to that, actually, this condition can always be fulfilled. You can always find endpoints satisfying this condition. Okay, so now that we have fixed all of this, let us state our result, and we will start with some uniqueness result. So the uniqueness result will be given as follows. So we fix L to be an integer, and we consider two quasilinear terms with a regularity that will depend on this L that we have fixed a priori. After that, the quasilinear term that we consider will satisfy the condition that I have introduced you before. We will pick our endpoint satisfying the geometrical condition that we have seen before and consider U of index J being the solution of this equation with the quasilinear term A replaced by the quasilinear term A of index J. And our goal will be the following one. What we prove is the following result. So provided that the conormal derivative of the two solutions coincide, for the parameter lambda lying on the interval minus RR, the parameter omega on the unit sphere, and the parameter tau in a sufficiently small neighborhood of 0, then what we obtain is that the differentiation with respect to eta at order k of the two quasilinear terms computed at lambda and 0 will coincide for lambda in the interval minus RR, and for this index k going from 0 to L minus 1, this L being the L that we have fixed in accordance with the regularity of our quasilinear term. So this L is proportional to the regularity condition that we impose. And the first question that we may ask ourselves, so okay, this is some kind of identification result. And when does this result lead to full uniqueness result? So the answer will be given by this corollary, where we show that actually if you improve the regularity into an infinite smoothness, and you add an analyticity with respect to this variable associated with the gradient of the solution, the same kind of data, you get the full recovery of the quasilinear term. So you need this extra analyticity dependency with respect to the variable associated with the gradient of the solution in order to get a full uniqueness result from this property. So this is the first result that we have obtained. And the first thing is that I say that we consider either n point or 1 point. The idea is that if instead of this general matrix valued quasi-linear term, you consider a real valued one, namely you consider quasi-linear term depending, taking the form of a real valued map times the identity matrix, then you can restrict the measurement to any arbitrary point at the boundary of your open set. So the point can be chosen arbitrary and only 1 point. And with that, and the same kind of condition with the conormal derivative, we can get exactly the same result. So if your quasi-linear term is a real valued one, you just need one arbitrary point for the location of the measurement. So this is for the uniqueness result. And what I would like to say is that actually here we have achieved at least one of the expected goal is that to make important restriction on the data used so far for this class of inverse problem. So here, actually, what I mean in terms of restriction is for the determination of nonlinear term that does not depend on space, of course. Even in that category, we make important restriction because when it depends on space, you cannot really make the comparison here. So I consider only comparison of this restriction of the data with the nonlinear term that does not depend on the space variable. So the important restriction, as I said, are first of all, Dirichlet excitation lying on the space of real valued affine function, which is of dimension n+1, which is of finite dimension, while all other results consider infinite dimensional space, and location of the measurement at n point, either 1 or n, depending on the type of quasi-linear term that we consider. While for quasi-linear term, so this is not the course, this is not the situation for semi-linear term. So for quasi-linear term, I have not seen any result dealing with point measurement, but for semi-linear term, there is result in that direction. So this part also is an important restriction comparing to what has been done so far for the determination of the quasi-linear term. So actually here, either you consider the excitation or the measurement. They are much more suitable for numerical reconstruction. Moreover, the type of excitation that we consider are not specific function, but quite well-known real-valued affine function, which are quite classical set of functions. So I think that comparing to what has been done in terms of connection with the numerical reconstruction, we are at least close. So this is the first thing that I wanted to say, but even in the theoretical setting, we make some improvement. And the first improvement, in addition to this restriction of the data, comes from the fact that we obtain, as far as I know, the first result about determination of a matrix valued quasi-linear term combining these two dependency with respect to the solution and the gradient of the solution. Okay, so this is about the uniqueness result. Now let me move to the stability result. So here for the stability result, the first thing that we need to do is to give more precision about the type of data that we will use. So again, we consider the solution of our boundary value problem, which will be a map with this different index giving the different dependency. And what we can look first for is that provided that you have access to quasi-linear term with some extra regularity, you will find that this extra regularity can be associated with your solution as a map, as its dependency with respect to this parameter tau. So this dependency with respect to the parameter tau will be of regularity CL, provided that your quasi-linear term is of regularity C2 plus. So this is the first thing that we can say. And now that we have this type of regularity, actually, we can show that the conormal derivative of the solution of our problem computed at this different point has a map with respect to the variable tau will be of regularity CL, and we can consider in terms of data the differentiation of this type of map with respect to tau at order k going from 1 to L to be the measurement that we will consider for our stability result. And our goal will be actually to determine this type of quasi-linear term from the corresponding data that we have seen, namely this type of data. So we start with a stability result for general class of matrix valued quasi-linear terms. So we restrict ourselves to matrix valued quasi-linear term of the following form. So we have a real valued part, which will depend on the solution and on the gradient of the solution, and a matrix valued part, which will depend only on the solution. So we impose also some extra regularity condition, which extra a priori condition, and which will be an estimate of the quasi-linear term with respect to a map C. So this will be used a little later on in our stability result. So the stability result will be divided into two parts. The first part being associated with the determination of this map B. So we have here actually a quite good stability result. It's almost close to the best you can expect. It is a Lipschitz stability estimate about the determination of this matrix valued function with respect to the differentiation with respect to tau of the conormal derivative of the difference of the solution computed at this n different point. So we take here the supremum of this data with respect to the parameter lambda from minus r to r, omega lying on the unit sphere, and the maximum for this n different point located at the boundary of our open set. And what is quite interesting here, and we will discuss about this a little later on, is that this constant depends only on the dimension of the space, the open set omega, and the n different point that we have considered for our measurement. So this is about the determination of this part where you have the dependency with respect to the solution of the equation. But if you want to determine about the information related to the dependency with respect to the gradient of the solution, that is this variable eta, you need to consider something different in a sense that you will have a stability estimate, which will degenerate from the Lipschitz one to a Holder one. And in addition to that, your constants have much more dependency. So this is the second stability estimate that we obtain. We consider here as the differentiation with respect to eta at order capital N of the real valued part of our quasi-linear terms, which will give us actually here symmetric tensor of rank capital N, and the norm with which we estimate them is norm of the tensor of rank capital N. So we consider the norm of usual norm of tensor of rank capital N. And this will be upper bounded by Holder, some kind of Holder estimate of data involving the different differentiation with respect to tau of order k going from 1 to capital N plus 1, of the difference of the conormal derivative of the two different solutions computed at this n different point of the boundary where we consider our measurement. So here you have different kind of dependency of the constant involving some a priori information about the quasi-linear term that we have considered, but also this parameter R, which is the set where we consider our stability estimate. And this is actually something that can appear in a quite natural way for this kind of stability estimate, since we try to estimate an unbounded function that can be actually unbounded. And if you try to have stability estimate for something that is unbounded, you need to consider local stability estimate. So this comes from the idea of having some kind of local stability estimate of this type of quasi-linear term. We do not have a global one. We have a local one, and this is related, as I said, to the fact that we deal with something that is not bounded. Okay, so this is the first class of stability estimate that we obtained. But again, we can improve all of this if we deal with quasi-linear terms, which are real valued, instead of considering matrix valued quasi-linear term, in a sense that we obtain similar type of result, except that the measurements are considered at one arbitrary point located on the boundary of our open set. Apart from that, you have exactly the same kind of situation. But this is the kind of stability estimate that we obtain. And here, what I would like to say about this result is that, first of all, concerning the first Lipschitz stability estimate that we obtained, we have here actually some confirmation of what I've already observed in my work of 2023, is that for this first part, that is the determination of the part that depend only on the solution of the equation, we obtain a Lipschitz stability estimate without any dependency with respect to the quasi-linear term under consideration. But this gives us actually some robustness property of the stability estimate in a sense that it has only dependency with respect to the open set and the point where the measurements are located. So we do not need any a priori estimate or any a priori information on the class of quasi-linear term under consideration. This is actually somehow, at least I have not seen something comparable in terms of stability. So this is the first thing that we can say about our result. The second one is that, so of course, this will not be preserved if you move to the additional information that we want to determine. First of all, the Lipschitz stability estimate will degenerate to an older one. And moreover, we need some a priori information about the class of quasilinear term for this next step, that is determination of information of the quasilinear term and its dependency with respect to the gradient of the solution. However, we still deal with Holder stability estimate, and we are still in a much better situation than what is usually considered for elliptic equation, namely logarithmic type of stability estimate. So the result actually that we obtain here can be more compared with determination at the boundary of coefficient in the spirit of some work of Alexandrine. Here, actually, we deal with something that can be compared with this type of a result. And this is the main reason why we deal with something that is much better than what is usually considered for elliptic equation, namely Lipschitz and Holder stability estimate. In addition to that, what is interesting for our initial proposal, namely moving to the numerical reconstruction, is how this stability estimate can be used for improving the numerical algorithm that would be used for the reconstruction of this type of parameter by means, for instance, of method like Tikhonov regularization, right? It has been proved by means of the work of Cheng and Yamamoto how the stability estimate can be used in order to consider suitable regularized parameter. So this is what I wanted to say about the stability result. Now, let me move to the idea of the proof. So, roughly speaking, the idea here will be to consider our data, that is the conormal derivative of the solution of this boundary value problem for this different set of parameters, and compute it at this n different point, x1 to xn, with the condition that we have seen before. And actually, what we will be interested in is the asymptotic behavior of this type of data for tau going to 0. We would like to see what will be the asymptotic behavior of this type of data and to extract from the asymptotic behavior of this data the information that we need for the determination of the quasilinear term. And we will see that actually this asymptotic behavior with respect to this small parameter tau will give us exactly the information that we want for the determination of the quasilinear term. So for this, let us start with the asymptotic as tau goes to as tau goes to 0. So let us see what happens when tau goes to 0. For this, let us recall that the conormal derivative of the solution of this boundary value problem takes the following form. So if you choose tau to be 0, you will have this type of expression where u of index 0 will be nothing but the value of this boundary value problem when tau is equal to 0. But if you take a look at what happened at the boundary when tau is equal to 0, you will see that actually the boundary condition will be this constant lambda. In addition to that, this constant lambda is solution of this equation. So what happened is that actually, if tau is equal to 0, your map will be nothing but this constant lambda, and its gradient will be equal to 0. So this means actually that in this expression, this gradient will be completely equal to 0, and we will have that our asymptotic properties for tau going to 0 will be exactly equal to 0 at order 0. So the order 0 is not enough. We need to extend this asymptotic property, and the extension will be given by Taylor formula. And through Taylor formula, we will see that this asymptotic properties at order 1 will be given by this differentiation with respect to tau of the conormal derivative of the solution of this boundary value problem for tau being equal to 0. So this is the coefficient that will give us the information about the asymptotic properties of the conormal derivative of our solution as tau is going to 0. So we need to determine that guy in order to being able to have this asymptotic property. So to determine that guy, what we need to consider is actually what is our conormal derivative and how, what will lead its differentiation with respect to tau. So the conormal derivative is a product of two functions, and its differentiation with tau will give us these two different expression. And here in these two different expressions, we will have u of index 1, which will be the differentiation with respect to tau applied to the solution of this boundary value problem for tau being equal to 0. So we'll have here the first differentiation with respect to tau, which will appear on that side. And again, what we will use is actually the fact that this guy is a constant, so this gradient is equal to 0, which will tell us actually that the only part that will remain in these two different expressions will be this one. And in all of this, we can replace u of index 0 by lambda and the gradient of u on index 0 by 0. So we'll have this explicit formula. And the only part that is remain in order to have something completely explicit here will be this expression, namely the differentiation with respect to tau for the solution of this boundary value problem when tau is equal to 0. This is the only part that is remain in order to have something completely explicit. So let us consider what is this guy, and let us see actually what will give us to apply differentiation with respect to tau and to fix it as tau is equal to 0 for the solution of our boundary value problem. What happened actually is that we will have access here to this boundary value problem, to a solution of this boundary value problem, namely an elliptic equation with constant coefficient and a boundary condition which will be linear. But what happened is that actually this map, this linear map, is again a solution of this elliptic equation with constant coefficient. Combining this with the uniqueness of the solution of this boundary value problem, what we have is that actually this map U1 will be explicit and it will be exactly the linear function that we impose at the boundary. And thanks to that, we know also that its gradient is this constant vector omega that we have imposed at the starting point through the excitation that we have applied at the boundary of our open set. So now we can see that actually everything will be explicit, and the asymptotic behavior at order 1 will be given by this explicit expression involving the outward unit normal vector, the quasilinear term, and this vector omega that we control through the boundary. So we will have here something completely explicit, and the idea will be that actually we have access to the asymptotic behavior of this data for our two different quasilinear terms. So this means actually that we will have access to this data for the two different quasilinear terms. Either you consider it in terms of uniqueness or stability. The situation is quite comparable. And the corresponding things that we determine, information that we determine, will be completely given by what we have here. So now the idea will be to combine this with the geometrical condition that we have imposed, which will allow us to move from this information to the different coordinate of this vector into this orthonormal basis, E1 prime until En prime, and then to move to the knowledge of this vector by means of this coordinate, since we deal here with an orthonormal basis, and to use finally the fact that we consider we have this for all possible direction omega on the unit sphere, which will allow us to fully recover this matrix valid map at lambda and 0. So this is the first step in our process of determination of this quasi-linear term. Now let us move to the next step, and the next step actually will be quite comparable in the sense that we will extend these asymptotic properties, asymptotic behavior of our data, not at order 1, but at order 2. We will extend it to what happened at order 2, and in order to have this, again, by means of Taylor formula, you know that you will have a coefficient that you need to obtain explicitly, which will be the differentiation at order 2 with respect to tau applied to the conormal derivative of the solution of our problem computed at this different point for tau equal to 0. So let us see what will be that guy. And the idea actually would be to see that if, again, we apply a differentiation with respect to tau at order 2, we will have a first term, which will be the differentiation with respect to eta of our quasi-linear term, which will be the new expression that will appear in our asymptotics, the one that is still unknown in this step of our process. Another expression h, which will depend only on what we have already recovered in the first order asymptotics, that is only the dependency with respect to the quasi-linear term computed at this lambda and 0, so no information about what happened with respect to this extra variable associated with the gradient of the solution, plus an expression which is still not explicit, which will involve on this U of index 2, where U of index 2 will be the differentiation with respect to tau of the solution of our boundary value problem at order 2 for tau equals to 0. So again, we need to see what will be that guy. And what happened again is that this guy will be a solution of a linear elliptic equation with constant coefficients. With this time, a right-hand side term that appears, where we will have the divergence of a vector valued function, which will correspond to this expression, and a Dirichlet boundary condition, which will be equal to 0. So what happened is that this expression, capital K, will be given by a constant vector plus a vector K prime, where actually K prime depend only on the parameter that we have determined in the first step. Namely, there is no dependency with respect to differentiation with respect to eta of our quasi-linear term, which is the new expression that we want to determine. But since here, actually, this vector is constant, if you take the divergence of K, you will have a divergence of K prime, which means that what we have on the right-hand side does not depend on this new expression. And the same will be true for U2. So at the end, the conclusion is that our asymptotic properties with respect to tau as tau goes to 0 of order 2 can take the following form. We have the new expression that we wanted to determine, that is a differentiation with respect to eta of our quasi-linear term, computed at omega and applied to omega, that we take the scalar product with respect to the outward normal vector computed at this different point, plus an extra term, which will depend only on what we have recovered in this first order asymptotics. So here again, we compare the asymptotics for the two quasi-linear terms, and it will allow us to determine that guy, this new expression. And now the idea will be to determine from this new expression the differentiation with respect to eta of our quasi-linear term. And we will do that again by using our geometrical assumption, the assumption that we have imposed on our quasi-linear term. It will be required here. In order to get this differentiation with respect to eta computed at omega. And finally, we use the fact that here omega is arbitrarily chosen on the unit sphere in order to determine the differentiation with respect to eta of our quasi-linear term. And we will proceed that way by iteration in order to get the differentiation at any order. And what we can recover again by the study of the asymptotics of our data as tau goes to 0 is the differentiation with respect to eta at order capital N of our quasi-linear term computed at the same vector omega, but omega can be arbitrarily chosen on the unit sphere. So now the idea will be to combine this with our assumption on the quasi-linear term and use a polarization argument in order to determine from that guy the differentiation with respect to eta at order capital N of our quasi-linear term. So this is the different step that we use in this idea of asymptotic study of our data. And what I would like to say is that actually this idea that we use here and this asymptotic property can be compared to one of the most important techniques used for the determination of nonlinear term, that is this linearization approach. So this linearization approach has its first formulation that goes back to the work of Isakov, who have considered the linearization at order 1, extended to the linearization at order 2, given by the work of Sun and Ullmann, and finally the linearization at any order considered by the work of Kurilev, Lassas, and Ullmann in 2018. So this technique has been intensively used in many works. So here, without being exhaustive, I mentioned several of them, dealing with the determination of nonlinear term. But here, what I would like to say is that what differs with all this approach and what I introduced here is the idea that in all this approach, the main goal was to transform the determination of this type of nonlinear term into some properties of density of product of solution of linear elliptic equation. But this is not what we are considering here. We have considered a completely different way to see these linearization techniques, mostly by considering the asymptotics of our data and to extract the information related to the asymptotics of our data for determining the corresponding quasi-linear term, which will appear actually explicitly in these asymptotic properties of our data. So this is the main reason why actually we do not use the Dirichlet to Neumann map in contrast to all these works, So of course, here actually I've mentioned result dealing with nonlinear term that has also the space dependency, but even for nonlinear term that does not have this space dependency, the approach that has been used can be compared with this type of ID in a sense or another, that at some point you use this type of density property or something that can be related. So this is what I wanted to say about this work. So in terms of prospect, there is actually several ones that I could mention. This idea actually of restriction of the data, we have also used it for the determination of a semi-linear term in some recent work, but I will not mention it here because things are not yet completely clear what we would like to, what we are doing with this work. But so here I will focus only on one important direction that I would like to take through this work, one important prospect, that is move from the theoretical result to the numerical reconstruction. So as I said, we have made here important restriction on the data that we have considered. We have good stability result, and I believe that at some point this can be used for numerical reconstruction. So we need to adjust the techniques that are used for the numerical reconstruction, like Tikhonov regularization approach, in this specific context of this asymptotic properties of our data. So for instance, comparing the asymptotic of the data, asymptotic coefficient of the data in order to get this type of numerical reconstruction. Or maybe otherwise, this is still an open part, an open extension of this theoretical result. And this is something that actually interests me quite a lot, to being able to have this theoretical result that can fit numerical reconstruction. So in addition to that, there is also another type of interesting extension of this work is actually to move to system of elliptic equation, like for instance, Lamé system, and try to determine quasilinear term for Lamé system with this specific type of dependency or other type of dependency, but try to use the same kind of ID in the same spirit with these asymptotic properties of the data that will allow us to determine the corresponding quasilinear term. Okay, so this is what I wanted to say. Thank you for your attention.
Thank you very much, Yavar, for the very nice talk. Thank you so much. Are there any questions or comments, please?